the probability that the verifier is convinced is bounded by some small error, epsilon sp. Again, we'll cover knowledge soundness. Informally, knowledge soundness says that a malicious prover that is able to convince a verifier somehow knew a corresponding witness for the instance. Formally, we define this using an extractor. So what we'll do is we look at a specific instance X. We look at a specific malicious prover P tilde that is going to run the interaction. We collect this interaction in a transcript alpha1 row alpha2. And then we say there exists an efficient extractor. Here specifically, we look at rewinding extractors that takes the instance, a transcript, and has a black box access to the prover and is able to output a witness. And we say that the probability that the verifier accepts, but that the witness that is outputted by the extractor is not in the relation, so it's not a valid witness, is also upper bounded by some error kappa sp. Just for some details, it's not super relevant in this section, but you might want to know this in general. Before, the soundness only depends really on the specific instance we look at, or even in general, you can define it to just depend on the size of the instance. Here, the knowledge error depends on the instance, but also on this delta quantity here, and this is a failure probability. This is just kind of quantifying how convincing a prover is. So for any instance, that might be, in the language or not in the language, this is the probability that the verifier is not convinced is going to be upper bounded by delta. So if you look at an instance that is in the language, the verifier will always be convinced, so delta is going to be 0. If you're considering specifically the good prover, the honest prover that is defined by the Sigma protocol, and you look at an instance that is not in the language, then this is going to be at least 1 minus the soundness error, and otherwise it might be something else. Again, this is not going to be super relevant for today. It's just kind of a question of definition, and it's good to know that this will also kind of influence the knowledge soundness specifically. And then the third definition that we look at for today is zero knowledge. So zero knowledge is kind of defined formally slightly differently than the soundness and knowledge soundness, because we talk about kind of zero knowledge. We talk about simulators. That's the best way to formalize those. So specifically, we define a view. So we take a prover, we take a verifier, we take an instance witness, and we define the view to basically be the transcripts. So what the verifier is able to learn from the interaction, everything it has access to. And then we require the existence of a simulator that only takes the instance. So in particular, the simulator does not know anything about the witness. And we say that these two distributions, so these are going to be distributions over some potential messages and potential challenges. These two should be very close in statistical distance. Specifically, we quantify how close they are by this value ZSPX, and this is going to be the zero knowledge error. So this is how we define zero knowledge. So those are the definitions that we'll look at. Are there any questions about the definitions or about Sigma protocols before we dive into the actual technical content? Nope. Okay. So the roadmap for today. So we've seen what a Sigma protocol is. We're not going to give specific examples, but these are very useful in general. For example, for proving knowledge of a pre-image of a commitment, or the things that involve signatures, and we're going to transform those into non-interactive arguments in the ROM. And we look at soundness, knowledge soundness, zero knowledge, and see how they transform when you apply the Fiat-Shamir transformation. And then we'll wrap up with looking at the state restoration property, which is kind of a very nice theoretical tool that will help us in doing this translation from interactivity to non-interactivity. We're only going to cover this part up until the random oracle model. Typically, the way you would apply this in practice is by heuristically instantiating the random oracle with a specific hash function. And so what this allows you to do is to go from an interactive argument to a non-interactive argument in the ROM to a non-interactive argument in the standard model that is heuristically secure and that you can actually run in practice. And the heuristics don't really kind of change the parameters. So the parameters you'll get here in the standard model are going to be essentially those that you get from the theoretical exercise. That's why we kind of focus on the theory without kind of going further on the practical side. But I'll give some tips on parameters and kind of concrete things you have to keep in mind when you do practical applications.
Can I ask about the definitions part?
Sure.
I just wondering if those applies to interactive and non-interactive in the same way.
That's a good question. Mostly, yes. So there are some syntactic changes, of course. So what changes specifically? For example, if we look at soundness here, row here wouldn't be sampled at random, right? Because and in particular, the prover is not able to be, we don't have interaction, so the prover will output a single proof. But you can replace for the non-interactive case this entire thing by a prover being output by, proof being output by the prover that is run on the instance, and then you replace the transcript by an actual proof. So this is how things would change. And similarly for completeness, and you would have the exact same things for knowledge soundness and for zero knowledge. Yes.
Thank you.
Any other questions? All right, so we'll focus first as a warm-up on the case of non-adaptive security. So in cryptography, there's kind of always this notion of adaptivity that you can consider. What non-adaptivity means is you fix a specific instance, and the adversary is not able to kind of tamper with that instance. This is kind of set before the prover and the verifier interact, and then at the end, you kind of are able to say something about soundness or knowledge soundness. What we consider after is adaptive security, where the prover and the verifier interact, but maybe the prover is able to influence the instance. For example, it only sends the instance at the end of the interaction. Or maybe if you have public parameters, it's able to first see the public parameters and then is able to choose an instance that it wants to do an attack on. Non-adaptivity is always easier than adaptivity, so we'll start with that, and then we'll see how we can strengthen the protocols that we have to achieve adaptivity. So we'll start with the construction, right? Kind of a compiler that takes a Sigma protocol and outputs a non-interactive argument. And a very natural protocol is the one in figure 9.1. So before we had these red things, right? So before the prover would send the first message, and then the Sigma protocol verifier would sample a uniformly random row and send us to the SP prover. What we're doing now is we're simply replacing this. We're replacing the choice of randomly sampling from the verifier by the random oracle that we assume here. So instead, we feed this alpha1 message into the random oracle F that was kind of sampled uniformly at random earlier at setup. Kind of just lives in the sky and we're able to query it. That allows the prover to non-interactively get a challenge that is going to be randomly distributed. And then the argument prover here is able to, just run the SP prover as a black box and get two prover messages, alpha1, alpha2. And that's going to be the proof. And then on the other hand, on the argument verifier, we'll do basically all of that and unpack it for the SP verifier. So we'll pass the proof as two messages. We'll derive the same SP randomness by querying the random oracle again. And then we'll just run the SP verifier with the instance and the transcript. So this is going to be exactly the same as before. We just kind of replace random sampling by the random oracle, which is kind of a very natural thing to do. Are there any questions about the constructions themselves? All right. So the first kind of sanity check that we want to do against this construction is if it's well behaved, in the sense that if you give me a Sigma protocol that has some soundness error, can I say anything about a soundness error of the non-interactive version that I just constructed? And we'll start with a lower bound, and this is lemma 9.2.1. This lemma says that if you give me a Sigma protocol for some relation that satisfies this mild condition, to which we'll come back later. There's some mild condition that you can assume the Sigma protocol satisfies. Then, if I construct the argument as defined here above, I can say that the soundness error, non-adaptive soundness error of the argument is going to be at least t times the soundness error of the Sigma protocol minus, t choose 2 times the square of the soundness error. T here is a specific parameter that we'll use for the adversary, and this is a query bound. So in the Sigma protocol world, the adversary is not restricted. The adversary is all powerful. It's able to, compute as long as it wants. It just has to interact with the verifier. When we go to the non-interactive setting, we have to restrict the argument adversary somehow. So we don't restrict the adversary on running time or resources or space. Instead, we just say it has a maximum amount of query it can make to the random oracle, and this is going to be fixed. It's going to be t. So what this is saying here is that, if you give me, maybe it's easier to see it here. If you set t and epsilon sp to be such that t times epsilon sp is smaller than 1, right? So you can think of t being, somewhat large, maybe 2 to the 80, epsilon sp being very small, maybe 2 to the minus 128. This equation above, says that the soundness of the argument is going to be at least t half times the soundness of the Sigma protocol. So in some sense, you're not kind of gaining any soundness. In fact, you're losing soundness, and you're losing soundness kind of linearly in the query bound of the adversary. This is just what this lemma says. Now, this lemma hinges on the small condition that we imposed on the Sigma protocol. And this requirement says, there exists at least one instance that is not in the language. And for this kind of specific instance, this is very convenient for the proofs. For every possible first prover message, so every alpha 1 in the set of bits, the probability over just sampling some random challenges by the verifier, the probability that there exists a second prover message that makes the verifier accept is exactly the soundness error. So this is kind of a simplifying assumption that we make. The reason why it's there is not too important. It's just kind of very convenient for the proofs to assume that there exists such an instance. And in practice, this is a condition that is satisfied by very, very natural Sigma protocols that you might come up with in practice. And I'll show you immediately how to use this. So if we want to look at this proof, what we want to talk about is this probability. So this is going to be upper bounded by epsilon nog of x. So this is the probability that the argument verifier accepts, given that we sample a random oracle at setup, and then we ask a malicious prover p tilde that has access to this oracle access to this random oracle to output us a proof.
Excuse me.
Yes?
Two quick questions. I hope they are really small.
Yeah, go ahead.
About the query bound, when we uh, see it from a practical standpoint, is it basically a hash rate, a number, kind of velocity with which attacker can brute force the hashes?
So it's related to the hash rate. It's not exactly the hash rate. So the way we typically set T in practice is if this limits the amount of queries that the adversary is able to make to the random oracle. When we instantiate the random oracle with a specific hash function, a reasonable way to set this in practice is to say, okay, what is a reasonable bound on the number of hash function evaluation that my adversary is allowed to make? And so you can look at, for example, okay, what is the combined power of the Bitcoin network over the last 10 years or 20 years? That's kind of a reasonable estimate. Or you look at some specific hardware and you say, okay, how many hashes can you do per second, and how many seconds have elapsed since this hardware exists, and how many more seconds am I expecting the protocol to go on? And that's kind of a good upper bound for how much hashing power the adversary has, and how much kind of random oracle access the adversary has. Typically, people set this to be 2 to the 64 if you're not too conservative, to 2 to the 80 to 2 to the 100 in practice. So you can think of this as being like roughly 100 bits large if you're very conservative.
Yeah, thank you. That's a great context. And another one, if it's easy enough, could you give an example of that of the element that you were talking about just recently when presenting this presupposition which we take?
Sorry, I don't think I got the.
Yes, 9-1. I mean, is there an easy example that you could give for 9-1?
I don't think I can give an easy example without specifying a Sigma protocols, and that would require pulling in a whole bunch of crypto. So I don't think I can give you a very quick example on the spot without bringing in a lot of additional background on
Okay,
crypto.
I see.
But
Then
the intuition is, there's kind of the soundness error says, okay, the probability of convincing a verifier is kind of always below some threshold. And what this is saying is that, well, there's kind of one instance that is exactly at the threshold. For this instance, for the specific instance, for all possible prover strategies for the first message, you cannot hope to convince a verifier with probability more than epsilon sp. Kind of exactly. So there's one instance that kind of matches this bound. Maybe the intuition will become more clear when we do the actual proof, right? This kind of 5-line proof here. So what we want to bound is the soundness error of the non-interactive argument, which is exactly this thing here. That's what we defined earlier. So what you can do is you can substitute the definition of V that we have from the transformation that we introduced. So this is just saying, okay, well, I know the proof is actually a tuple of messages, and I'm just going to run the SP verifier on those messages, and the challenge is going to be the random oracle output on alpha 1. And you can define, this event here. Let's see, this event here to be a concatenation of some random variables. So you can define those random variables xi that say, okay, I know the prover is going to make at most t queries to the random oracle. Call those alpha 1i. And for each of those, you say there's a random variable xi that corresponds to the verifier, on this specific try that the adversary is doing, being convinced. Right, so in some sense, the argument adversary has kind of t queries it makes to try and figure out something out about the random oracle, or about the verifier strategy. Declare a random variable for each of those tries. And then you can do a simple inclusion-exclusion principle by saying, okay, so the probability that the argument is convinced is the probability that at least one of those t tries convinces the SP verifier. And what is this going to be? So it's going to be at least the probability that any one of those convinces this minus the intersection. So this is the intersection to make sure that we're kind of covering everything. And so this part is just going to be t times the soundness, right? Because it gets t tries. And if we want to tighten the bound somewhat, we can say, okay, well, there's, t choose 2 indices ij in t that are distinct. And for those, probably there's no overlap is going to be epsilon squared. So this is just to have a tight result. You can also kind of just ignore the second term if you want to be a bit sloppy and just say, well, the lower bound is t times the soundness of the sigma protocol. So this is just kind of a first sanity check to try and understand what this transformation does and how it behaves. In particular, it doesn't boost soundness, but there's a lower bound that says, well, there's somehow the argument in the sigma protocol soundness errors are closely related by a factor of t. The kind of dual is, I think, maybe more interesting. The dual lemma sets an upper bound on the argument. So this is kind of more interesting in practice because what you're saying here is that the argument soundness is going to be at most t plus 1 times the sigma protocol soundness. So in particular, if you set this to be 2 to the 80 bits, for example, and you know that this is your sigma protocol is going to give you, I don't know, minus 200, like 200 bits of security, then what you can say is you have, 120 bits of security for the argument itself. So this is saying, okay, the maximum amount of security that you're going to lose concretely is going to be just a factor of t. It's going to be exactly the query bound. And if you combine this with the lower bound that we had from before, you kind of sandwich this argument soundness error between this upper term and between this lower term that also depends on the sigma protocol. So in some sense, the kind of attack that or the prover that we constructed above is kind of optimal in some sense. And there's a really tight security relation between those two terms. I don't think I'll go through the proof of this inefficient reduction because it's, I think, slightly artificial from the tools they use. I think I want to focus a bit more just on the general technique of the efficient security reduction, which is kind of something that you'll see more in the, I think, in the following sections of the book, and is also kind of a standard tool in cryptography. But first, are there any questions about the statement of the lemma? Okay. So as a reminder, we're just trying to say, we know that this, the probability of this argument verifier accepting for a proof given by a malicious prover is going to be at most t plus 1 times the probability of the sigma protocol verifier accepting given a sigma protocol prover. And in particular, it's not any sigma protocol prover, it's one that we construct. So if you give me an argument adversary that kind of breaks soundness of the argument, I'm able to return a sigma protocol adversary that is able to break the sigma protocol soundness. This is kind of a standard reduction in cryptography. The way this works is you basically just run the argument prover. So there's some subtleties. For example, for the random oracle, you might remember from the lecture last week that if you want to store a random oracle, it's very big because it needs to take potentially unbounded inputs. So instead of just storing this oracle, because we want to be efficient, we will lazily sample an oracle. And the way this works is you sample an empty table, and for every query to the oracle, you sample the random value, and you keep track of it in the table. So you're really kind of just building up the random oracle as you go, and so you don't need to store all possible entries. You just need to store, at most t plus 1 of them in this case. And so the way this SP prover works, it just runs the argument prover, simulates a random oracle to it until this adversary outputs a first query alpha 1, roughly. There's going to be some more details, but until it outputs a first prover message. Then, the SP prover expects a first prover message. You just output this that you send to the verifier that lives here over the edge of the screen. And the verifier is going to answer with a challenge. And then you feed this challenge into the random oracle. So instead of, doing the interaction with the prover, you program the random oracle to be this challenge at the value alpha1. And then you query the argument to the prover again on this value. And at some point, the prover is going to give you another value alpha2. That's the high-level strategy. There's, some small details. In particular, PTL here might not be well behaved. So it might, for example, refuse to give you a first message. Or it might, do queries that you can't really pass as a message. In this case, you need to be a bit more careful. So this is why we kind of sample this index as part of all the queries, and then we'll simulate it up to one query, and then we'll take that message to be correct. That's kind of a more technical detail on the proof that I don't think we have time to go into. The core technique is that you have this kind of equation here that you can basically say that this is fine. This is kind of the probability of the prover not behaving nicely for the reduction is going to be 1 over t plus 1. And then if you do the complete reduction, you just kind of follow up these arguments, and you can conclude that the argument soundness is at most t plus 1 times the sigma protocol soundness. So I know I went over the proof rather quickly. I think I just wanted to give you more of the high-level idea of how reduction works, because we're going to be using this again in the following section. I think that the exact details of the proof are a bit slightly too involved for this kind of format, but I think with this intuition in mind, you should be able to go back over the actual proof and just follow along and see, okay, how do they specifically break down the adversary and relate these two things. But the core idea is that you can build a Sigma protocol prover that behaves very closely to a good Sigma protocol prover that is able to convince the verifier even for an instance not in the language, given that you have this argument prover that is also good at convincing an argument verifier about the instance not in language. So that was soundness. We can do the similar things for knowledge soundness. So knowledge soundness, you also pick up a factor of t plus 1. Again, very briefly, here you also have a similar kind of construction. So here, we kind of do the opposite, right? We're saying, okay, assume that the Sigma protocol is extractable. Assume there's an efficient extractor, ESP, that takes an instance, a transcript, and has black box access to a prover and is able to output a valid witness. Well, you can simply wrap this around, and construct an argument extractor that takes an instance, a proof this time, and the transcripts that correspond to the argument kind of interface. And here you only get an argument prover. So in order to feed an SP prover to the SP extractor, we're just going to construct this malicious SP prover. And this is going to be exactly the construction that we've seen above. So we'll just reuse the reduction from above. And we'll say, well, if I'm given a good enough argument prover, I'm able to build a good enough Sigma protocol prover, and I can just feed this to extractor, and the extractor is going to give me a witness, and I can just output this witness. And the loss that I incur is very similar to above. I also incur a loss of t plus 1. Now, additionally, there's some other losses that are kind of hidden in this running time. So this is the expecting running time of the Sigma, of the extractor, of the argument extractor. And now this is going to be the extractor of the Sigma protocol. But in addition, we will pick up an additional factor. So if you remember, the extractor kind of took this failure term. So now we put this additional failure term that is also dependent on t. And then because we need to do some random oracle programming and queries, we'll also pick up this factor r times t. So r here is the output of your random oracle, and t is the number of queries. So this is just to say, well, the runtime slightly increases. But still, these two things are, closely related by a factor of t. And then, for zero knowledge, things get even easier. So zero knowledge kind of is a direct reduction. So if you have a good simulator for a Sigma protocol, you have a good simulator for the argument. So you can see this here, right? The way we build the simulator is you first run the SP simulator to get a simulated view, an instance, and a simulated transcript. You set the proof to just be the corresponding values of the interaction. And then mu here is kind of this interface to program the random oracle. And what you're going to do in the simulator is you will plant the random oracle to say that, well, actually f of alpha 1 should return rho, just so that the verification passes at the verifier. And so, you just say, well, if I have a simulator for the Sigma protocol that does all the heavy lifting. Somebody has proven that a specific Sigma protocol has a good simulator. All you need to do really when you go to the random oracle with this construction is to program the random oracle to match that interface, to make the verifier accept. That's it. Again, for the proof, there's kind of a slightly more detail, but those two things are very closely related. So that was about non-adaptive security, which is kind of the warm-up. Next, I'm going to look at adaptive security and see how, in turn, adaptive soundness and adaptive zero knowledge do break for the simple construction that we've looked at, where you just kind of hash or feed the first message to the random oracle. Is the broad intuition of how kind of going from an interactive argument to a non-interactive argument preserves soundness up to a multiplicative factor of t. Okay, I think this was the heaviest proofs for today. The rest is kind of just variation on the same idea, so I won't go into technical details, just give you the high-level intuition. But first we want to see, okay, what happens when we now have adaptivity? So if you remember, if you look at a Sigma protocol, this is it. You have 3 messages. Let's look at a specific Sigma protocol that's going to completely break under an adaptive adversary. This particular Sigma protocol doesn't really look at the first message. It samples a random challenge, and it only accepts if the instance matches this challenge. So for a given instance, it will only accept if the randomness that it randomly generated matches the instance. So it's not a very good Sigma protocol. It's not very useful. It still has decent soundness error, right? So the soundness error is is due to the -r. Because you're sampling rho at random, the probability of the instance matching this is going to be 1 over 2 to the r. So what happens when we do the construction that we had above? So if we remember, we built a argument prover and argument verifier, and instead of doing this interaction, we feed this into the random oracle, and the random oracle is going to give us the rho. So what happens now? Well, there is a very simple attack. So here what the adversary does, it just samples an alpha 1, runs it through the random oracle here to get a rho, and then after that says, you know what, actually the instance I was thinking about is exactly the rho that I sampled. Because I'm not constrained to set the instance at the beginning, I can just set the instance to be whatever I output here. And then the proof is going to be alpha 1 and alpha 2. And now the argument verifier is going to take alpha 1, run it through the random oracle again, get rho, and lo and behold, rho matches the instance that the prover has announced. And so here, the soundness error is 1. The malicious prover is always able to find an instance X that convinces the verifier with this proof. And particularly, you notice that this doesn't match the bound that we had before, right? So particularly what we showed before is that in the non-adaptive case, this should be t plus 1 times epsilon sp. And here the prover only makes 1 query to the random oracle, so we can even restrict the prover to only have one query, You would expect this to be, something like 2 times the soundness from before, 2 times 2 to the minus r. Obviously, this is not bigger than 1. So, what allowed the adversary to break adaptive soundness is that it has the ability to decide on x after the interaction has run, or after it's kind of computed a proof. So kind of looking ahead, the way to fix this is to artificially force the adversary to, in some sense, commit to the instance before it does any of the interaction or any of the random oracle querying for the actual proof. So in particular, what we'll do, we'll see this later on, is that we also require the instance to go into the random oracle. And if you've read any of the, there's roughly 1 or 2 papers a year on, how people mess up Vietnamese in practice, and they kind of miss some parts of the transcript of the instance or the public parameters into the transcript. This is exactly such an attack. If you don't include the instance in what goes into the random oracle, you allow yourself to an adaptive attack. So that's for the soundness part, right? You need to make sure that everything goes into the transcript. There's also an issue with zero knowledge. So again, we'll look at a specific Sigma protocol that is kind of degenerate, but illustrates why this breaks in practice. So in this Sigma protocol, we have 2 messages. We completely ignore these messages, so you can assume that those are 0, for example. The verifier will sample a row, we'll send this over. And here, if you assume, for example, that the relation is easily decidable, it's something in P, the verifier will just exhaustively check whether there's a witness for X. So for, assume we have a relation that is trivial, and the verifier, interacts with the prover, but that's kind of completely useless. It will just decide based on the instance. And, this will have some zero knowledge error, ZSP. So again, the way we build these provers, right? We'll build an argument prover and an argument verifier, and we'll feed A1 into the function, and we'll get a challenge. So what is an adaptive attack here? So what you can do as an adversary is, in the first stage, so here the adversary is the verifier, right? So in zero knowledge, we assume the prover is honest, and the verifier is malicious, and it's trying to distinguish between kind of a simulated and a real world. So it's trying to verify whether it's interacting with the prover that knows something about the witness, or with a simulated that doesn't know anything about the witness, and thus kind of has zero knowledge of the witness. So in the first kind of stage of the adversary, it's going to choose, kind of adaptively, an instance and a witness, such that the instance is actually in the relation, just so that the verifier will accept later on. And it will just store for later the random oracle evaluated at 0, and 0 here being kind of a placeholder for the alpha1 value that the honest prover will send. And then this is kind of the setup, right? And then during the distinguishing phase, the adversary will just check whether querying the random oracle again is going to be the same value as it stored before. If yes, then this is going to be real. This is going to be the real world, because the random oracle doesn't change, right? When you query the random oracle twice on the same value, it's going to give you the same answer. However, if the random oracle now suddenly says something different for 0, then the adversary now knows that it's in a simulation, because the simulator doesn't do anything about the random oracle. It samples those values at random. It doesn't have any information about what f of 0 should be. And so here, there's a very easy way for the adversary to distinguish whether it's actually running with the prover or whether it's actually running in a simulation. Right? This doesn't mean that the adversary is kind of able to learn anything meaningful from the witness, about the witness from the prover. It's just saying that there's kind of a break in distinguishing capabilities. In particular, you can say that the zero knowledge error of the non-interactive argument is going to be at least 1 minus 2 to the minus r. So it's just the probability of not hitting a collision with the random oracle value here. So again, there's going to be a fix that we'll kind of look at later on that Fiat-Shamir implements. The capability here hinges on the fact that the value of the random oracle is kind of easy to guess in some cases for the first prover message for this adversary. So what we can do instead is we can make this value hard to guess. So we'll add the random salt tau here, and we'll just say, well, okay, actually the challenge should be the random oracle queried on the first message and this random salt. And because this random salt is going to be sampled at random by the prover, it is also going to be sampled at random by the simulator, it's going to be really hard for the adversary to distinguish, or to guess what it should kind of output here to check whether it's running in the real world or in the simulated world. That's the high-level intuition. Are there any questions before we go into the actual Fiat-Shamir transformation? So just to recap, we started with this kind of very simple construction that just considered the first message. It gives you, soundness, knowledge soundness, zero knowledge in the non-adaptive setting, which is already pretty good for the fact that you're just kind of replacing a random sampling with a random oracle. However, when you want strong guarantees in practice, like non-adaptive adaptive guarantees, this it does fail. So for this, we need to be a bit more clever about the construction that we do, about the compiler, and this is the Fiat-Shamir transformation for Sigma protocols. And this is exactly basically the concatenation of the two fixes that we discussed. So given an SP prover, the way to construct an argument prover is to let the SP prover output the first message. You then build this thing. So this thing in particular, it has the instance in it to prevent the adaptive attack on soundness. And it also has this salt T, that is tau, that is sampled uniformly at random. And then you do what we did before. You input this into the random oracle, you get a challenge, you feed this challenge into the SP prover, you get a second message. And the proof now is alpha1, alpha2. But also the randomly sampled salt, because the verifier needs this to do its own query. And then we parse this as two messages and a salt. We feed this into the random oracle, we get a new challenge, and we just feed this into the SP prover. So that's the Fiat-Shamir transformation for Sigma protocols. And this is kind of a very nice transformation because it also preserves a whole bunch of efficiency metrics that we care about. So for example, the proof is almost the same size as the SP proof. So in particular, you're only sending the two messages as before, and the only addition that you're sending is the message tau. So that's the size of the proof that the prover has to send. Then for the prover, you just have to run the SP prover. In addition, you make a single random oracle query that has size, size of the instance, size of the first message, size of the salt. And same for the verifier. The verifier just does the SP verifier and does one random oracle query of this size. So if you think, concretely, this thing is going to be, I don't know, maybe 64 bits, a few bytes, compared to whatever the SP proof is going to be. And if you think in concrete terms, the non-interactive argument prover is going to be your SP prover, and the only cost you're going to pay in addition is a bit of hashing. So that's the Fiat-Shamir transformation. And then what we can show is that the things that we've had before kind of carry over nicely in the adaptive setting. So the proofs look very similar. What we have here is that the argument, the adaptive soundness error of the argument is at most t+1 times the soundness error of the Sigma protocol. And so I don't want to go too much into the proof because, again, there's a bunch of details that are kind of not super material to the day. But this is a very similar strategy. You can kind of bound the probability that the adversary doesn't play nice with the reduction with a very similar lemma as before. And again, you need to lazily sample the random oracle for this reduction to be efficient. You can also do the same for knowledge soundness. So here's the thing that the knowledge soundness error of the argument, now we have a bunch more parameters because we want to be more precise than before, is also going to be at most t+1 times the soundness error. Again, we have this kind of interesting shift of failure probabilities that are also kind of dependent on this value t. In practice, this is something that you take care of with concrete parameters. And the runtime of the extractor for the argument is also going to be the runtime of the SP extractor with these kind of new parameters. So again, you pick up a small factor here, which is just from doing this additional random oracle queries, and you pick up this failure error here. And the proof is very similar. We use this small lemma that relates the two, and then you build the extractor in a very similar way. So you first, given an argument prover, you build a malicious SP prover that is good and security relates closely to the argument prover, and then you just feed this to the SP extractor, and you're able to relate the two efficiently. So again, I'll skip the proof. The proof is very thorough. I encourage you to have a look at it, kind of after, between now and the next meetup, which is going to be in 2 weeks, just to get a bit more kind of comfortable with the intuition. But if you only take away the high level takeaway, I think that's going to be very useful for example, concretely setting parameters. And finally, zero knowledge. Here things get a bit more interesting. So before we didn't have this factor t over to the s. Now we have the zero knowledge, kind of the argument being upper bounded by this sigma protocol soundness, sigma protocol zero knowledge error, plus a distinguishing advantage, which is going to be the number of queries times 2 to the s, which is the salt space. So if you think of it, right, now we're kind of sampling a random salt and we're feeding this into a random oracle. And if you apply the attack from before, which is going to kind of somehow think as being optimal, the only way to distinguish between those two is to just query t things in the random oracle, trying t out of these 2 to the s possible salts. And maybe you get lucky and you find the one that was used by the prover. And in this case, you're able to distinguish whether you're in the real or the simulated world, or you don't, with probability 2 to the s minus t over 2 to the s. And in that case, you're not able to distinguish those. Formally, we do this using hybrids. So we have a real distribution, which is going to be the adversary running against the honest prover. There's a hybrid where we have this kind of short kind of simulator that still has access to the witness and still, kind of runs the SP prover. But instead, it programs a random oracle using the salt sampled at random. So it doesn't take the salt from the prover, it kind of generates a new one. And the distinguishing advantage between these two is going to be exactly this t over 2 to the s term. And then you can show that these two, when you replace the actual prover by the simulator that doesn't know the witness anymore, this is exactly the zero knowledge error of the sigma protocol. There's nothing about the argument here anymore. And so we kind of nicely decompose these two terms. So that's kind of the high level ideas. So maybe the one line takeaway of this section is that at least for sigma protocols, there's a very simple construction, the Piaget construction, that takes an interactive argument and gives you a non-interactive argument that preserves soundness and knowledge soundness and zero knowledge nicely. And the price you pay is directly related to the number of queries to the random oracle that the adversary is able to make, which is something that you can reasonably control and cost in practice. However, you might have noticed that, the proofs are kind of, they're very specific for sigma protocols. And they, for example, they make this assumption that we had earlier, and they're in general not the nicest to work with. And if you, kind of looking ahead in 2 weeks from now, you can imagine that this is going to be even more complicated when you look at multi-round protocols, where you potentially have many different rounds, and you need to argue about what's happening in each round, and how these kind of probabilities work with each other. So this is why the book discusses this notion of state restoration soundness, which is kind of really central in the book and is a very good formal tool to analyze those kind of protocols. And I just want to show you the state restoration game as a high-level idea. The idea is that this is a notion that is kind of a direct translation of what you would expect security to look like when you look at an interactive argument that you applied Fiat-Shamir to. So what this is saying is you have a malicious prover for a Sigma protocol, and it's kind of against the state restoration game. And this prover is able to run against a challenger, and for at most t times, it's able to send an instance, a first message, and a salt to this challenger. And the challenger is going to initially sample a random function, right? So kind of a random oracle of its own, and it's just going to answer these random oracles. So this is just capturing the exact same interface as the random oracle, just as a challenger, and we have the same bound. And then at some point, the state restoration prover is outputting an instance and a full transcript, right? So this is very similar to the proof that we had in the non-interactive case. You output 2 prover messages and a salt. The challenger samples the corresponding challenge and outputs this. So this is just kind of really modeling the power that an adaptive prover has when it knows that it's kind of running in something that is going to be compiled with a random oracle type construction, like the Fiat-Shamir transformation. And I'll skip those definitions. You can generalize this to state restoration knowledge soundness and to kind of with rewinding and straight line flavors. The core lemma is that the soundness error of the argument is directly related to the state restoration soundness error of the Sigma protocol. Because we kind of really targeted the definition to be about something that is a Sigma protocol that is going to be applied, that is going to go through Fiat-Shamir, and that is then going to be an argument. And you have the same for knowledge as well. And so before we kind of had a direct proof, now we're kind of decomposing these two things. And then what you can show kind of as a second step is say, okay, so this state restoration soundness things is actually related to the standard soundness of the Sigma protocol using this factor of t. So before we had kind of epsilon arg small equal t+1 times x minus p, and now we kind of introduce this intermediate notion that is kind of really targeted towards the goal that we have as a stepping stone. Yeah, and so I don't want to talk too much about state restoration. I think we're also out of time, but this is going to be a recurring theme in the rest of the book. And it's going to be especially important in 2 weeks from now for the multi-round case. Are there any questions kind of maybe on the high level things? I'm also happy to dive into more technical definitions or proofs if you're interested. But I think it's more important that you get the high level intuition for how Fiat-Shamir works and what the pitfalls are when you try to compile an interactive argument into a non-interactive one. I see somebody's typing, so I'll wait until the question comes. Otherwise, yeah, feel free to leave the channel, maybe go over to the ZK hack kickoff. I'll just stay around for a few minutes if you have any specific questions.
No question from me, but let me thank you for the session.
You're welcome. Yeah, I hope it wasn't too rushed. Again, this is 30 pages of technical content that we have to go through in an hour, so it's going to be a bit compressed. But hopefully you have the high-level intuition for the rest of the book as well, and the idea of a reduction and of kind of composing extractors together.
Yeah. Thank you.
Yeah.
Bye.
Thank you.
Thank
Goodbye.
you very much. Yeah.